everyone, and welcome to our discussion on carbonyl reactions. Today we're going to talk about addition reactions to carbonyls and specifically to hydrates. This will serve as an introduction to general addition reactions and have a specific example, and then from there we can expand this to acetals and imines and more complicated examples. So hopefully this is helpful. So before we get started in the reactivity of these things, we just want to have a general introduction to aldehydes and ketones. They do work a little bit differently than some other things that you'll see. For example, it's different than carboxylic acid derivatives, okay? So we do need to know the nomenclature for these. I'm not going to go into a whole bunch of detail in class, but I'll give you some resources for that. But just so you recognize, we are doing aldehydes, as you can see over here, and then ketones on the right. Those are the functional groups. They can obviously have more carbons attached, but that's what the general functional groups look like. Just like all the other functional groups, they have their own particular endings. So aldehyde, the ending is going to be Al, and for ketones, it's going to be one, O-N-E. They have the same naming rules of everything else we've done, so just like we started out with alcohols and moving on from there, they have the same naming rules. The only thing that's different is they are a priority functional group, so you need to know the priority. So they're higher than alcohols, but lower than carboxylic acids and their derivatives. So just FYI. We're not going to generally have things with two different types of carbonyl functional groups in the same molecule, so you probably don't have to worry about that right now, but just so you know in the future. The last thing I'll mention is that you do need to know a few common names. These are common names that you would see very regularly, so you would see them perhaps on like standardized test in a different subject, something like that. So I want to make sure you recognize them, and those will all be on the practice that's on Blackboard, and also there's a video link on Blackboard if you want to see more about the naming. All right, so that's all I have to say about naming for right now. So let's get started into the bulk of what we're going to talk about today, which is, of course, the reactions. So we're talking about addition reactions, but since we previously talked about nucleophilic acyl substitution, it makes sense to compare them first before we move on. So our previous reactions that we did, like I said, are nucleophilic acyl substitutions, like you see. Those all had leaving groups, right? That leaving group might be an OH, that leaving group might be an O carbon group. So those could be amides and esters and anhydrides and chlorides, any of those things. But all of those things had in common was they had a good leaving group. So when you were trying to predict the product, you're basically going to take the leaving group and it's going to leave, and you're going to replace it with a nucleophile. That's the definition of substitution. Something goes on, something comes off, and it's generally kind of equivalent, all right? And then if we remember, the mechanism starts with the nucleophile attacking. Now, there may be another step before that, right? We might have to do some like tricks, but generally the nucleophile is going to attack the electrophile at the carbonyl carbon. Electrons are going to go up, and then some stuff might happen, and then electrons are going to come down, and the leaving group is going to leave, and that's how you get that product, right? Okay, so addition reactions are somewhat similar, but a little bit different. So let's look at some examples. So now let's see what happens if you have either a ketone or an aldehyde. They're going to be really similar. So basically, the difference between these reactions now is that we don't have a good leaving group. So it's really important to know that carbon and hydrogen are never going to be a good leaving group. That's really different. So there's no way we can make them into a good leaving group. That's just never going to happen. So the nucleophile is still going to attack at the carbonyl carbon. So let's look at that. So if the mechanism, sort of partial mechanism, would be the nucleophile here is going to attack at the carbonyl carbon, electrons are going to go up, just like we saw before. Okay, so that part's similar. But now, whenever we get our tetrahedral intermediate here, it's going to be a little bit different because there's not anything that can readily leave. So generally, one of two things can happen. The first thing is you can just add a hydrogen and get an OH here. That's what we're going to see for a hydrate. So basically, this is the general mechanism that we'll see similar to our hydrate, except for obviously we skipped some steps. We didn't show like making things not a leaving group. We didn't show where the hydrogen came from, so we'll show those details. But for right now, that's the general idea. The other thing is that sometimes we can have, since the nucleophile is not going to leave and the carbons can't leave, you can make this OH actually be a good leaving group, right? That's possible. So that's what we're going to see whenever we look at acetals and imines, which are a very popular reaction that we're going to see a lot. So we can make that leave. It's just you have to do some extra work to do that. So we'll show that later. But today we're just going to focus on the first step. So that's what the general mechanism would look like for the ketone. It's very similar for an aldehyde, but we'll see that the product looks a little bit different. So basically it's going to look like this. So we start with our aldehyde, our nucleophile attacks, we get the same sort of intermediate, and then whenever we draw the product, it just is not going to be showing that hydrogen because generally you don't show hydrogens on line bond form. So it just looks a little bit different. Just know like that hydrogen's still there, it's just not being shown. So now let's look at an example with a specific nucleophile. So let's talk about making a hydrate. So a hydrate is something that you actually get anytime you have a ketone or an aldehyde in water. You're going to get some amount of this hydrate. It's in equilibrium, so you may see a lot of it or a little of it depending on the structure and what's sort of around it, basically. So there is some equilibrium going on there. You don't have to show the equilibrium arrow. I'm just letting you know. So some of these are mostly in the ketone form and some of them are mostly in the hydrate form. It just depends on what you have. So let's look at how this mechanism would work. So the first thing is we need to know, like, we're in acidic conditions. So as we've said, acidic condition means you can do a couple of things that you couldn't do if you were in basic conditions or neutral conditions. So let's talk about those. So as we said, when you're in acidic conditions, there's certain things you can do with the mechanisms. So one of the things you can do is make a better electrophile. So that's something we're going to do. Another thing you can do is make a better leaving group. Now, if you notice in this case, we're not going to be doing that because we have two O's and one of the O's is actually we started with. So we're not going to make a good leaving group now, but we'll see that again later for acetals and imines. One of the other things we notice when we're in acidic conditions for the mechanism is that we're only going to see charges that are positive or no charge at all. We're never going to see negative charges for an acidic conditions situation. So that's a good way to check yourself and make sure you're doing it right. So now that we've sort of reminded ourselves about that, let's go ahead and look at the mechanism. So the mechanism for making a hydrate, as we said, is acidic. So that means the first thing that we can do is make a better electrophile. We have a weak nucleophile. We have a not great electrophile, so we want to make it better. So how do we make an electrophile better? Right? So what we're going to do is we're going to add a proton, right? So the very first step is going to look like this. We're going to have this be our nucleophile here, and then we're going to add a hydrogen, right? It's going to be an acid-base reaction. And that acid is just coming from the solution, so it's okay just to draw an H+ since we're in acidic conditions. You don't have to show it being attached to anything. All right, so let's draw what the product of that looks like. So it would look like this, and then we would have a charge. So where would our charge be? Right, we're going to have a positive on that oxygen. So now that we've made a better electrophile, the next step is going to be the nucleophile attacks the better electrophile. That's the whole point of making it better. So our nucleophile, remember, is going to be this water. So we'll draw a lone pair there. And then it's going to attack. Now, where's it going to attack on here? The carbonyl carbon, right? That's the same thing. So we're going to attack the carbonyl carbon and the electrons are going to go up. And that's just like all the other reactions we've seen so far with carbonyls. So now let's draw what the product of that would look like. So it'll look like this, right, with all our pieces. Okay, and so then the next thing that we're going to do is figure out what we need to make the product. So looking forward, what do we need to make the product now? Right, so we're going to keep one of the OHs, but the other one just has to lose a hydrogen. So that's going to be our last step. So then that's just going to be a strong acid-base reaction. And then we're drawing that in acidic conditions. So we're just going to draw one arrow. You don't have to show it comes to get the hydrogen. You can just draw it like this now. Shortcut. So that's the whole mechanism for making a hydrate. It's not very long. But before we move on, let's talk for just a second about how you would be able to predict what the product was if you didn't have the product shown. So generally what I do is I just number the carbons. So it would look like that on the left, right? And then on the right, what is this carbon with the two O's going to be? What carbon would that be? Right, it's going to be carbon 2. So that's what we see. We're going to start calling this the key carbon. So maybe I'll highlight that. So key carbon, and then I'm going to highlight it. So any sort of reaction that happens is going to happen at the carbonyl, and keeping track of that key carbon, that where the carbonyl was, will help us keep track of what our products are. And that makes it a lot easier if you know what you're sort of looking for. So that's our key carbon. So just keep a lookout for that. So we've seen a hydrate with a ketone. A hydrate with an aldehyde works exactly the same way, it'd be the same mechanism, but it's going to look just a little bit different. So if we have an aldehyde like this, so I'm just using a generic aldehyde, then the hydrate would look like this. So notice I've got the same thing before. I've got the key carbon where the carbonyl was. That's where the OHs are going to be. The only thing that's different is there's just not the hydrogen shown here. There is a hydrogen there, you just don't have to show it like you do whenever it's on the aldehyde part. All right? So hopefully that makes sense. You can see how they're related. As always, if you have any questions, just let me know for our next class. So that's all we have for today. I hope you enjoyed this video, getting an introduction into addition reactions, and check out Blackboard and see if there's any activities you need to do, and I'll see you in class. Bye.